In this EzEd video lecture, we are going to take a look at equilibrium of coplanar force systems, wherein we learn about free body diagrams, their importance, and the method to draw them, types of supports and reactions, types of beams, and also types of loads.
Seriously, pay attention. This is important.
We will first learn about free body diagrams. Consider a lamp of weight W, suspended from two strings, OP and OQ, tied to the ceiling. If we want to analyze the force system that is acting on the lamp, we need to isolate it from the wall. Such a diagram of an isolated body with the representation of all external forces acting on it is called a free body diagram. The free body diagram of the lamp will show the weight W of the lamp acting vertically downwards and the tensions T, OP and T, OQ in the strings OP and OQ respectively. We will now study about the steps to construct a free body diagram. Consider the book resting on the table. The first step to construct a FBD is to determine the body to be isolated. In this case, it is the book. Next, we isolate the body with a diagram that represents the complete external boundaries. In the third step, we represent all forces that act on the isolated body in their proper position with the diagram. Although the book is stationary, two forces are acting on the book to keep it stationary. One is the weight W of the book exerting a force down on the table. The other is the force extended up by the table to hold the book in place. This force is known as normal force N and is equal to the weight of the book. In the final step, we indicate the choice of coordinate axis directly on the diagram. Thus, we have learned the method to draw a free body diagram. Let us now learn about supports and reactions. Consider a boy is sitting on a chair watching TV. His weight is being supported by the chair, which offers a force of resistance, reaction upwards. When a body is supported with the help of a support, like a wall, floor, hinge, or any other body, the support offers some resistance to the body, known as reaction. The following are the different types of supports and the reactions that they offer. Let us first take a look at a roller support. A roller support is free to roll on a surface on which it rests. A roller support can be represented by any of the following three symbols. It only offers a force reaction normal to the surface on which it rests. Next, we learn about hinged supports. A hinged support allows free rotation of the body but does not allow any linear motion. It is represented by this symbol. Consider the hinged support at A. A hinged support offers a force reaction which can be split into a horizontal and vertical component. Consider the pin which connects a door and a wall. It allows rotation of the door but allows no linear movement. When two bodies are connected in such a way that the connecting body allows rotation between them and thus behaves as a hinge, then such a connection is called as an internal hinge or a pin connection. Hence, the pin is an internal hinge. A fixed support neither allows any linear motion nor any rotation. Consider the fixed support which connects the bar to the wall at A. A fixed support offers a force reaction which can be split into a horizontal HA and vertical component VA, and also a moment reaction MA. Consider a lamp is suspended by two strings. A string, rope, cable support offers only a pull force in a direction away from the body. This force is also called as tension force. Hence, both the strings exert a tension force on the lamp. Now, we will learn about beams. A bar subjected to forces and couples that lie in a plane is called a beam. Beams are structural members which offer resistance to bending. The various types of beams are as follows. The first type is the simply supported beam. When both ends of a beam are simply supported, it is called as a simply supported beam. Such a beam can support load in the direction normal to its axis. Now, we will take a look at beams with one end hinged and the other on roller support. If one end of a beam is hinged and the other end is on rollers, the beam can resist load in any direction. The next type is the overhanging beam. If a beam is projecting beyond the support, it is called as an overhanging beam. The overhang may be only on one side or on both sides. Now, we will learn about cantilever beams. If a beam is fixed at one end and is free at the other end, it is called as a cantilever beam. A propped cantilever is a beam with one end fixed and the other end simply supported. Next, we will take a look at beams with both ends hinged. In these beams, both ends will be having hinged supports. The last type is the continuous beam. A beam is said to be continuous if it is supported at more than 2 points.
Hey, it's time to concentrate now.
The various types of loads that can act on a body are as follows. When force acting on a body is concentrated only at a point, it is called as a point load. Consider point loads F1, F2 and F3 acting on the beam. A force that is spread over an area is called as a distributed force. When forces are applied over a region whose dimensions are not negligible compared with the dimensions of the body, we must account for the actual manner in which the force is distributed. This is done by summing up the effects of the distributed load over the entire region. For this purpose, we need to know the intensity of the load at any one location. That is, we find the resultant of the distributed forces acting at a single point. These are the basic types of distributed loads. When a load of uniform intensity is spread over a length, it is called as a uniformly distributed load. Such a load can be converted into an equivalent point load by multiplying the intensity with the length. The resultant point load would act at the center of the spread. A rectangular load is also an example of a uniformly distributed load. Consider a rectangular load of intensity W acting on a length L. Its resultant point load and its location are as shown. When a load of a uniformly varying intensity is spread over a length, it is said to be a uniformly varying load. Consider a triangular load. A UVL can be converted into an equivalent load which is equal to the area under the load diagram, that is, half into W into L acting at the centroid of the load diagram. The centroid will act at a distance of 2L by 3 from the left end and L by 3 from the other end. A trapezoidal load is a special loading pattern. Here, the load intensity varies from a low intensity of W1 Newton per meter to a higher intensity W2 Newton per meter over a span of L meters. Thus, this loading can be divided into two parts, AUDL of intensity W1 and AUVL of intensity varying from 0 to W2 minus W1. Newton per meter, that is, a rectangular and a triangular load. The resultant point loads of the rectangular and the triangular load are then calculated. In this type of loading, the loading intensity varies along any curved surface. Consider a varying distributed load of parabolic nature. Such a loading can be explained by the equation of the curve, and its resultant point load is the area under the curve, that is, W into L by 3, and acts at the centroid of the load diagram, that is, at a distance of L by 4 from the right. The equivalent point load is as shown. Let us now take a look on how to find the resultant of a distributed load. The beam AB supports a load which varies in intensity. Calculate the magnitude and position of the resultant load. The loading pattern shown in this problem is a trapezoidal load. Hence, we will analyze it as follows. Firstly, we divide the loading into two parts. One, a rectangular loading on the bottom and a triangular loading on top of it. We will first find the resultant F1 of the rectangular load using the basic formula to calculate area, that is, base into height. Next, we find the resultant of the triangular load F2 using the basic formula to calculate area, that is, half into base into height. Then, we will add them to find the magnitude of the resultant. The magnitude of the resultant is calculated as 2400 newtons. Then, we use Vargnan's theorem to find the exact position of the resultant with respect to point A. On substituting the values and then simplifying, we find that the resultant acts at a distance of 3.5 meters to the right of A. Let's have a quick review of what we've studied in this lecture. The diagram of an isolated body with the representation of all external forces acting on it is called a free body diagram. We then learned the steps to draw a free body diagram. We learnt about the different types of supports and the reactions that they offer. We learnt about the roller support, hinge support, fixed support, and the cable or rope support. A bar subjected to forces and couples that lie in a plane is called a beam. We then saw the various types of beams. Example, simply supported beam, beam with one end hinged and the other on roller support, overhanging beam, cantilever, propped cantilever, beams with both ends hinged, and the continuous beam. Next, we learned different types of loads. When force acting on a body is concentrated only at a point, it is called as a point load. The force that is spread over an area is called as a distributed force. We then saw the basic types of distributed loads, that is, uniformly distributed loads, uniformly varying loads, trapezoidal loads, and varying loads.